This is Unsiloed, brought to you by Alumni FM, connecting people through stories.
Hi, welcome to Unsiloed. This is Greg LeBlanc. I'm here with Stuart Russell, who is in the engineering department here at UC Berkeley and is also the founder and director of the Center for Human Compatible AI at UC Berkeley. And of course, the author of this book, Human Compatible, which is it's a pretty amazing book. I really enjoyed it. You're also the author of some other books, including the textbook that everyone uses, the co-author of the textbook with Peter Norvig on artificial intelligence, which I actually left in my office. Normally I would have it with me and I would hold it up and present that as one of your other books. But we're going to focus primarily on this today. So welcome, Stuart.
Pleasure to be here.
So, one of the things that I found really interesting about this book is how interdisciplinary it actually is, and how much you draw from. I mean, kind of like Herb Simon, you draw on all of these different disciplines: economics, political science, epistemology, theories of intelligence and computing, and it seems like AI and machine learning now is kind of become a place where you have to really consider everything. It's really a place where you can't just simply pursue traditional computing methods, but you have to think about these broader issues. This is a relatively, I think, new development. I mean, people like Herb Simon and so forth have been thinking about these things, but do you think that to get a computer science degree, to think seriously about machine learning, you have to expose yourself to other insights to be a responsible practitioner, or is this something that only folks like yourself have to, you get to do all the thinking? Is this something that the ordinary students now have to start thinking about?
Well, I do think that computer scientists need to become more like doctors and civil engineers who take their ethical responsibilities very seriously. And that's because AI is moving out of the lab into the real world, and it's affecting people's lives, their livelihoods, the functioning of their democracies, and so on. So, in a sense, I think computer science students do need to understand more than their own technical discipline. And that's what one would expect for a discipline that starts to impact the real world. But I think there's more to it than that, because, the products of civil engineering, for example, the bridges, they don't think and participate and act in our democracy the way that some AI systems may be starting to do. So in the long run, if we are making things that function as if they were minds, I'm not going to say that they are minds, but function as if they were minds, then you're going to bring in all the considerations that have occupied philosophers and political scientists and ethicists for thousands of years about the place of human minds, how they should and should not interact with each other. So you have to understand all that. And then, there's also the fact that AI is kind of a universal tool that can be applied to pretty much every discipline that the human mind can be applied to, from poetry to construction to nuclear physics to climate science, and so that means that people who study AI are often going to be asked to participate in all these other kinds of activities. And so that's a fantastic aspect of doing AI, is that you have these opportunities to work in so many areas because AI is potentially useful for so many things.
Now, I've interviewed some other folks, including AJ Agrawal and others that do more kind of business applications of AI, and he of course is thinking about kind of machine learning as prediction machines, and if you view it in that narrow sense, then it's really kind of glorified Excel or Monte Carlo simulations or stuff like that. And if indeed it's just a tool that helps us to make better decisions, then a lot of the themes and issues that you raise are aren't that really that big of a deal. Could you walk us through maybe the history of AI? You talked about the various winters, and no one ever mentions the summers. They only mention the winters. But there's been some ice ages along the way. And how did we get to where we are? You mentioned that at one point when you were teaching at Berkeley, you had only 25 students in your class, right? It's so hard to
Yep.
imagine that this was such
Yep.
an arcane area.
I have 800 right now. So as you said, it's gone through ups and downs. I mean, the first big up and down, arguably, was in the 1840s when Charles Babbage developed his analytical engine, which was basically a universal Turing machine. So it had the full capacity to do general purpose computation. And Ada Lovelace, who worked with him on trying to develop programs for the machine, talked about the fact that it could be used for anything to which the intellect of man could be applied. So they pretty much had the idea that we could do AI with universal computers. And then the winter came, and since they couldn't get funding to actually finish the construction of their machine, and even if they had finished it, it would have been a bit too slow because it was 20 tons of brass wheels and cogs and shafts and things like that. So the real impetus for AI was a development of the computer in the Second World War, which arose from Turing's mathematical work, 1936 paper. And Turing himself, as soon as he figured out that you could actually start computing, and he understood this idea of universal computation, wanted to build intelligent machines. He wanted to write chess programs. He talked about doing machine learning. And very soon after the war, people were doing some pretty amazing things. So Arthur Samuel, for example, had a program that taught itself to play checkers at a quite impressive level of play, better than Arthur Samuel himself. And it learned that completely from scratch. And that was demonstrated on television in the late 1950s and caused actually some degree of alarm because it was the first proof that machines could go beyond what their creators knew how to program them to do. And that was always, when people worried about, the risks of creating intelligent machines, philosophers would say, of course, machines can only do what they're programmed to do, and so we don't need to worry. But of course, if they can be programmed to learn, then they can learn to do anything. And so that offers you no protection whatsoever. So the field took off in the in the late 1950s, early 1960s, with a lot of military funding aimed initially at machine translation, but also at the idea that you could use machine learning systems for various kinds of military applications. And machine translation was intended to translate the output of Russian scientific literature so that America wouldn't be caught by surprise, as happened with the Sputnik launch. But that turned out not to work very well. We had a very rudimentary idea in those days of what machine translation was. They basically thought you just looked up the words in the English-Russian dictionary and then sort of rearranged them into the right order, and you'd have a translation. And it doesn't work that way at all. So there was what we would now call an AI winter. They didn't call it an AI winter then because the phrase comes from nuclear winter, which was actually a concept developed around 1980 by Carl Sagan and others. And in the UK, there was a government report in 1973 called the Lighthill Report, which basically said, look, this AI stuff isn't going anywhere. We see one failure after another, and we recommend there should be, no government investment, and universities should stop working on artificial intelligence. So there was basically an official government ban on AI everywhere except Edinburgh and Sussex. And so this AI winter lasted until the early 80s, and then people started finding ways of using AI systems to solve what they called knowledge work tasks.
Mm-hmm.
So tasks where human beings use their expert knowledge to do useful things. And that could be medical diagnosis, it could be configuring computers, it could be, designing various pieces of equipment for oil platforms, et cetera, et cetera. So there were many, many hundreds, if not thousands, of these expert systems that were built. And in the mid 80s, AI was as popular as it is now. Roughly speaking, I remember the last term that I was at Stanford in 86, 10% of the student body took the AI course in that term. So it was really very, very popular. People had huge expectations. They had the same idea that if we just have, more, bigger machines, more data, more rules, we'll achieve human level AI and so on and so forth. So that technology turned out not to work very well in practice because they didn't really solve the core issue, which is in that reasoning in the real world requires handling of uncertainty. So dealing with probabilities, dealing with uncertain information. And the various kinds of rule-based methods that they had in the expert system industry simply didn't do that properly, which meant that as those systems grew, as you added more rules, the interactions between the rules would cause the system to just make terrible mistakes. You could fix a mistake on one case by changing the rule, and then it would break another case. And then you'd add another rule to try to handle that, and that would break a third case. And eventually, companies realized that the technology was never going to be easy to use, and certainly didn't scale up to large reasoning problems. So the second AI winter started probably around 1988. So I was hired at Berkeley in 1986. So I sort of came in on the crest of a wave, and then a few years later, AI was much less popular. And as you mentioned, I had 25 students, and I think 1991 was the nadir. But at the same time, so even though there was this AI winter, in fact, I remember going to a dinner with a bunch of Wall Street people, and we went around the table, introduced ourselves. I said, I'm Stuart, I do artificial intelligence. One of them said, oh, I thought AI failed in the 1980s. Which is an odd thing to say. It's sort of like saying, I thought physics failed, right? AI is a problem, not a technology. So it can't fail, right? It can just take longer to solve. And you wouldn't say physics failed because of cold fusion, right? So people have always had this strange idea, out in the outside world and the media, that AI is a technology. So nowadays, people often confuse deep learning and AI. So when deep learning fails, I'm sure that there'll be hundreds of journalists and pontificators and pundits saying, oh, well, now that AI has failed, it's time to go back to something else, right? Even though AI failed in real world applications, at least I should say expert system rule-based technology failed in the late 80s in real world applications. The field itself changed dramatically in the 1980s, going from, I would say, a field where logic and rules were the dominant paradigm to a field where uncertain reasoning using probability theory and decision theory became the dominant paradigm. And that's something that's actually much more familiar to economists and people in business schools, is the idea that you have models that predict uncertain outcomes, and you make decisions using expected value, and so on. So that paradigm, partly through the work of Yuda Perl, who developed Bayesian networks, that became dominant in the 1990s. And that allowed AI actually to then connect to all these other disciplines, to statistics, operations research, economics, game theory, etc., from which it had been completely separated. And in many ways, it almost created a continuum between the sort of probabilistic machine learning flavor of AI and what people do in statistics or econometrics. And you can see all of the benefits that came from that cross-fertilization. So yeah, it's an interesting question. So what's happened in the last decade is the development of deep learning, which actually arose in the early 90s from the neural network branch of machine learning. And the neural network branch of machine learning goes back to the Second World War, to work by McCulloch and Pitts, who basically proposed a simple model of the operation of neural systems by abstracting all the messy biology and saying, well, really, a neuron is just like a Boolean gate, except that it thresholds its inputs and then decides, if the inputs are above threshold, then I'm going to output a 1, otherwise I'm going to output a 0. But basically, they were saying the brain is a giant Boolean circuit made of neurons. So that was the first thing. And then the second thing was developing the learning rules, which were due to Donald Hebb, and Frank Rosenblatt, and others. So in the 1960s, the early versions of neural nets were being trained on image data and so on. They were trying to get it to recognize patterns and so on. So that didn't work too well because the networks were way too simple. It had a resurgence in the 80s when people figured out how to train bigger networks. If essentially they rediscovered the chain rule of calculus. Probably would have been easier if they had just applied the chain rule of calculus. But anyway, they rediscovered the chain rule of calculus and used that to train networks to fit data. So that led to a big resurgence of neural network research from 1985 to about 1995. And Jan LeCun and others at Bell Labs were using those networks to try to do handwritten character recognition so that you could process checks and letters in the post efficiently using machines. So it was a very, very narrow task, but the methods they developed were very, very general. They developed convolutional neural networks, which are essentially neural networks that are specialized to process images, taking advantage of the fact that the pixels in an image, the fact that those pixels are next to each other actually means something. So that the pixel features have spatial structure, and the convolutional network takes advantage of that spatial structure. So that was the core of what became deep learning. And starting around 2010, various groups tried to build bigger and bigger convolutional neural networks to solve both image recognition and speech, and had significant progress in both areas, partly because of the availability of larger data sets and much faster computing, including GPUs. But also we discovered a few algorithmic tweaks that we didn't have in the 1990s, such as stochastic gradient descent and rectified linear units, instead of sigmoids, and so on. So it was sort of like we already had the Ferrari, we just didn't know how to put it into fifth gear. right? We were driving around in first gear or second gear, making a lot of noise, but not making much progress. And then we found fifth gear, and this car is really great and it works. So it works pretty well for image and speech recognition, and that created this current explosion that we see now. So I guess you would say every time there's a small gain in function in one branch of AI, because of the generality of these techniques, there's a big explosion in economic interest as people see all kinds of things in the real world that they can apply it to. And that will continue to happen. Deep learning is just one step. There'll be another half dozen such steps. And each of those will probably increase the scope of applications by a factor of 10.
Now, one of the things that you talk about in the book is this idea of the Baldwin effect, right? Which is the trade-off between resources devoted to fixed rules and resources devoted to kind of learning. And I think this is an idea that I encountered in kind of evolutionary biology, right? Where you're trying to figure out how much of the behavior of an organism you want to hardwire and how much you want to make kind of context dependent in the service of the getting to the highest point of fitness. These ideas, I remember encountering these ideas in the late 90s and early 2000s, and talk was that if you wanted to solve a problem, the best way to solve the problem was a very complex problem was to have quite a bit of learning, environment-based learning, and then have some evolution kind of weed out the rules that weren't working. Was there cross fertilization in that area as well? Looking at how practices evolved through learning, whether at the genetic level or at the cultural level. I saw this as kind of a nature versus culture discussion.
It's an interesting question. I would say that the evolutionary computation branch of AI has largely remained distinct. They have their own conferences, their own journals, and you don't see very much cross-fertilization. So if you go to NeurIPS, which stands for Neural Information Processing Systems, that's the main machine learning conference these days, you'll see at most a handful of evolutionary computation papers. So sometimes people use evolutionary computation to design the structure of the neural network. So basically, if you take two neural networks and chop them in half and rearrange the pieces, that's a kind of evolutionary operation. And then you keep doing that, hoping that you're going to get some better result in the end. But by and large, evolutionary computation hasn't had a huge impact on mainstream AI, and it functions separately. But the idea that we should build systems by tabula rasa learning, that has gained a great deal of currency. And I would argue that that's probably, well, I wouldn't say probably, it is a huge mistake. Part of it is because humans don't learn by tabula rasa learning, right? A human that's brought up in isolation with no connection to other humans or civilization doesn't reach the frontier of theoretical physics. They don't even learn to use language at all. So the ability to learn depends to a large extent on the ability to apply what you already know to learn the next thing, and to learn it from a very small amount of data. So when you get a picture book to teach your child what different animals look like, right? There's one page with a giraffe. There's one page with an elephant. There's one page with a kangaroo, right? You can't buy picture books with 20 million pages of giraffes and 20 million pages of kangaroos, because human children don't need it. They need one, maybe two examples. And these are, cartoon pictures of kangaroos and giraffes. And then for the rest of their lives, children and adults are able to reliably identify kangaroos and giraffes in a huge range of lighting conditions and backgrounds and other objects and so on and so forth. So we have very robust learning from very small numbers of examples. And that's because we learn with the benefit of everything that we've already learned in the past. And this is where I think at the moment we just don't see these kinds of capabilities in deep learning systems. Deep learning systems don't really have a way to know things. They can't take in knowledge as an input, and they can't use that knowledge to reason or to learn. And those are basic capabilities. So my sense is that the pendulum will swing back. Maybe it already is swinging back, because we're seeing actually some of the frailty of the deep learning systems, that because they don't know anything, they learn in ways that a human would think completely ridiculous. So one example is if you look at the ImageNet dataset, which is for recognizing objects in photographs, it has lots of different breeds of dog, and the systems actually become pretty good at recognizing all these different breeds of dog. But then if you analyze, well, how is it recognizing, this golden Labrador or a golden retriever, right? Well, it's looking at the grass that the dog is sitting on, because in the training set, the retrievers are sitting on one kind of grass and the Labradors are sitting on a different kind of grass. So we're just looking at the grass and says, okay, well, if this grass is this color, then it's a golden retriever. It doesn't even look at any of the pixels that form part of the dog. If it's recognizing a parachute, it just turns out it's looking at the sky pixels, not looking at the parachute at all. Right. So if there are pixels, sky pixels here, and here, then it must be a parachute. And there's nothing wrong with that, right? It's taking the most obvious regularities that it can find to explain and predict the data that it's given. But that's not what humans are doing when they're learning to recognize a giraffe. They don't think it's a giraffe because the page is blue, right? They understand to some extent what it means to be an animal, what it means to be a physical object, the fact that categories of physical objects depend on, shape and coloring and that kind of thing. And so they quickly extract the general properties of the shape of a giraffe and the coloring of a giraffe, and now they have a robust giraffe classifier. And that's how humans learn.
Now, these problems that you're describing are the problems that bedevil any of us who are trying to work in, say, tool AI, right? Where we're just trying to solve a relatively narrow problem, classify dogs and cats and so forth. But I think the bulk of your book is really concerned with these much bigger problems that affect what people call AGI, right? General intelligence, or what happens when you try to create intelligent agents. And I thought that when I was reading through the book, I was thinking about it through the perspective of agency theory, right? So in economics, we're bedeviled with this idea of, how do you create an agent? Typically, it's a corporation or maybe an employee or an organization, and you want that entity to perform some kind of function, right? Perform some kind of goal, and you want to give it some autonomy so that it can utilize the context or the environment around it and learn from the environment. So at what point does tool AI become, general intelligence? What is there a discontinuity there, or do the concerns that you have, is it really more of a spectrum?
Yeah, so it's an interesting set of questions, because often you'll see this dichotomy being drawn in in papers that talk about the risks from AGI. They'll talk about tool AI or narrow AI as AI that's that's just being built to solve a particular problem, like recognizing dogs and cats or playing Go. And that's distinct from general, work on general purpose intelligence, and the former is safe and the latter is dangerous, right? And I think this is a huge mistake. If you actually go and look at what people do when they're doing tool AI, they are often, not always, but often developing technology that is applicable to general purpose intelligence. So where did deep networks come from? They came from Jan LeCun and his group at Bell Labs trying to recognize handwritten digits on checks, right? But the way they did it was not to write, okay, I'm going to write an algorithm that recognizes an S by finding a loopy bit and another loopy bit and seeing if the loopy bits are joined together in the right way. And then I'll write another algorithm for recognizing a 4, and that's got to have an uppy bit and a diagonally bit and a crossy bit, and they have to, right? That's not how they worked, right? They could have done that, but they had good taste enough not to do it that way. They developed an approach based on machine learning, and that produced convolutional neural networks. And that's what a lot of people are scared about these days. And the same with Go. In fact, the AlphaGo, which DeepMind developed and beat the human Go champion, is really the same program that Arthur Samuel developed back in the 50s to play checkers. It's just a bit bigger. Now, please, DeepMind, don't get upset. I don't mean to be criticizing, but the same basic approach is what we call reinforcement learning, where you just tell the program when it's won and when it's lost, and then it adjusts its processes for making decisions so that it wins more often. And reinforcement learning is also a big piece of the puzzle for general purpose AI. So working on tool AI, if what you're working on is a particular application that we don't yet know how to solve with existing methods, you're probably going to end up contributing to the progress of general purpose AI. So that dichotomy is not going to save us. You can't pass a law saying, as long everyone has to work on tool AI, they're not allowed to work on general purpose AI. That doesn't work. So I think, as I said, right now, deep learning is not the whole solution. It's a nice piece of a solution. It's nice to know that we have methods that can train these complicated circuits to fit complicated functions. But there are more breakthroughs that have to happen, and so in the book I outline some of them. But I think the biggest thing that we don't know how to do right now is what humans do naturally and seamlessly, which is to operate at many timescales simultaneously. From the timescale at which I'm controlling the movements of my tongue as I speak, which is on the millisecond timescale, all the way up to the timescale at which people choose to do MBAs or PhDs, which is multiple years, and PhD is approximately 1 trillion motor control commands that your brain sends out to all of your muscles over that 5-year period. And we don't think of this as a great skill that we have to be trained to do, or that we have to learn algorithms to do. It just comes naturally that we operate at all of these timescales. And coming back to the question of tabula rasa, I think our civilization, our culture, provides a lot of the higher levels of abstraction, so that getting a PhD didn't used to exist. Right now, it exists as a thing, and because it exists as a thing, you can choose to do it or not do it. Right, so your decision making can have this massive scope and scale. Because your civilization has made available many, many layers of abstraction, all the way from motor control commands up to these multi-year activities. And that's what to a first order thing, that's what makes humans so capable of functioning in the real world. Most animals don't have all those levels of abstraction, right? They have pretty much, as far as I can tell from my dog, they have today, or they actually just have like now in the last 5 minutes and then maybe the next 2 minutes. And so this is something that if we make this breakthrough, if we really understand how to have this seamless operation at multiple timescales, how to develop those levels of abstraction, build up and add more layers to it, that takes us a long way towards AGI, or artificial general intelligence.
Well, there are two big problems that you mentioned in one chapter of the book: the gorilla problem, which I think is really an AGI problem, but then the King Midas problem, which is something that exists at every level, right? Which is how do you specify the objective? And when I was reading some of your examples, one of your example was, you tell your assistant to, go fetch you a coffee, right? And then your assistant, disappears for a week, trying to find the coffee because you failed to specify that, only do it if you can do it in the next, 5 minutes, or, and so, iteratively you have to keep adding in these constraints and so forth. But this is exactly the problem we talk about in law, right? So there's actually a famous example called, the soup meat problem, where, you leave your child with a babysitter, and you say, go to the store and buy some soup meat to feed the kid. Okay, well, what happens if there's no soup meat, or what happens if and so oftentimes you'd say, well, all right, fine, don't specify. Just if the kid is healthy, you give them a reward. If the kid's unhealthy, you don't give them a reward, and let them figure out how to take care of the kid. And so in law, we talk about how if you really wanted to design an optimal agency contract, it would be infinitely long, because you'd have to specify every possible contingency, and that's obviously something that you can't do in the ordinary course of your daily life.
Yeah, I think there's a very close connection. So the gorilla problem you mentioned is sort of, how do we avoid the fate of the gorillas, right? And their ancestors a few million years ago, in some sense, decided to produce another species that was more intelligent, namely the humans. And now the gorillas are probably pretty annoyed about it, because they have no future unless we choose to allow them to have one. We don't want to be in that situation with respect to the machines. And strangely enough, even though Alan Turing, in his 1950 paper, the one that has what we call the Turing test, he's quite optimistic. And he looks forward to all the things we might be able to do with machines. In 1951, he gave a lecture on the radio where he said, basically, once the machine thinking method had started, our feeble powers would be left far behind, and we should have to expect the machines to take control. Just like that, right? So how does that happen? Right? The question is, as you make AI more and more capable, why do things get worse and worse and worse? Right? Normally we think of improving technology is just generally a good thing. But if your technology is based on the idea that you have to specify the objective, then, as you point out with the example of fetching the coffee, right? If you didn't specify the objective correctly, then you're basically setting up a kind of a chess match. Now you've got two agents, the machine and yourself, with conflicting objectives. There's what you really want, and then there's what the machine is pursuing, which is a poorly designed proxy. And as the machines get more intelligent, you come off worse and worse in this conflict, and eventually. Because the machine is, if it's designed that way, if it's designed to pursue the objective that's put in it, it will eventually find ways to increase the probability of success. It will find ways to control the rest of the world.
Hmm.
It will still get you a cup of coffee, but to avoid any risk of failure, it will take control of all the resources. It will perhaps eliminate any other entities in the world that could interfere with the fetching of coffee, and so on and so on and so on. So it's actually quite hard to even think of any fixed objective that doesn't lead
Hmm.
to catastrophically bad outcomes. When the
We wind up with a
machine,
world. We wind up with a world filled with paper clips, right?
whatever it might be, right? And people say, oh, of course, oh, that sounds silly, right? But
Mhm.
that example, which comes from the philosopher Nick Bostrom, is simply intended to show that um, it doesn't really matter what objective you put in,
Mhm.
that every objective is harmful if it's taken literally, right? So that comes back to this question of agency in economics. And for sort of the same reasons, economists have had to grapple with this idea that you've got some other entity, namely the employee or the subsidiary of your corporation or whatever it might be, and you would like it to act in your interests,
Mhm.
but either you write down an infinite contract, right, specifying exactly what that means in all possible circumstances, or you have to do something else, right, set up some kind of incentive mechanism. Um, the the difference with AI is that with economic actors, subsidiaries or employees, they have their own interests,
Mhm.
right? And so they're going to pursue their own interests. You just have to figure out how to shape the world so that them pursuing their interests ends
Mhm.
up benefiting you, right? So you shape the world by providing incentives, and then in pursuing their interests, they end up doing things you want. And of
So isn't
course,
it the same when I mean, isn't the idea of providing a reward to the agent in reinforcement learning similar to the idea of providing a reward to an agent in an organizational context?
to some extent, yes. So reinforcement learning is a little bit like that. But to do reinforcement learning, so if you think about how do you train an agent to play Go using reinforcement learning, you have to have a piece of code that can tell when the game is won or lost,
Mhm.
and then supplies a one or a zero to the reinforcement learning system. So that piece of code is an exact specification of the objective.
Mhm.
And the problem with human life in general is we cannot exactly specify the objectives,
Mhm.
right? And corporations can't really do it either, right? So they typically will have a proxy like, okay, well, how much money are you making for me?
Mhm.
And we'll give you a promotion based on some calculation of,
Mhm.
let's say it's a subsidiary. Okay, well, the subsidiary has to, deliver dividends or profits to the parent company, and then we'll reward the CEO accordingly, right? But this leads to all kinds of perverse
Mhm.
behaviors, um, accounting fraud, uh, externalities.
Mhm.
The fossil fuel corporations, they're just pursuing quarterly profit
Yeah.
objectives and destroying the world in the process. And so it's kind of like the paperclip example, right? If you think paperclips are impossible, then why don't you think filling the atmosphere with carbon dioxide is impossible, right? Well,
Yeah.
turns out that it is possible and it's happening.
Right.
So you better figure out how to deal with it. So what I'm arguing in the book is that um, we can't provide direct incentives in the way that
Mhm.
reinforcement learning does, because to do that requires knowing what the objective is.
Mhm.
Um, and so we have to have our machines that operate with explicit uncertainty about what it is that humans want.
Mhm.
And I think you could also look at solving principal agent problems that way in economics.
Well, I thought about that when
Except
you
for,
talked about. when you talked about the principles of the ideal agent, I was thinking these are the principles that you would want for your ideal personal assistant or for your ideal employee, if you could design one.
Yeah, if you could design one, and that's the key point, right? We can't solve the economic principal agent problem, by stipulating these three design principles, because we don't actually design the employee, right?
Mm-hmm.
Whereas we want to design the AI system so that it's actually constitutionally constructed
Mm-hmm.
to satisfy these three principles. So the principles are basically that, number one, the machine's only payoff is the human payoff function, right? The second principle is the machine doesn't know what the human payoff function is, and the third principle is that the machine can learn about what the human payoff function is from evidence provided by human behavior.
Mm-hmm.
So that kind of grounds this notion of payoff in a way that the machine can then learn more, sort of at runtime, as it were, about what it's supposed to be doing. And that can be, so we can take those principles and formulate them in game theory. We call them assistance games, but it's just a particular kind of game where the machine has a prior probability distribution on what the payoff function of the human is, and then you solve the game. And in particular, you write the machine algorithm so it's solving its half of the game, and then you look at the results, and you see that machines that solve this game are provably beneficial to humans.
Mm-hmm.
Whatever whatever human preferences actually are, then the machine will be beneficial in expectation to the human. I mean, early on, when it doesn't know anything, it's going to behave very, very cautiously. It might ask you a fair number of questions about your likes and dislikes and ask permission before doing things. But then as it learns more about your preferences, it'll become more and more useful.
Mm-hmm. Well, there's two steps there that you make. I mean, one is thinking about there being a single individual human with a single individual agent, and how it would make sense to design the agent to satisfy the preferences of that individual human. But then you kind of make another leap, which is, well, let's imagine humanity, and we've got these agents of humanity, and of course there's a lot of additional problems when you make that second leap. But just with the first leap, I mean, with the first step, when you're designing an individual agent, as imagine just your personal assistant, there you still have quite a few problems. You mentioned, I mean, the King Midas problem, of course, is one, but then also you have this problem of kind of wireheading. And I was wondering, this is a problem that comes up all the time. Danny Kahneman talks about it. I mean, in behavioral economics, behavioral finance, there's a lot of discussion about this, certainly in the psychology of well-being and happiness. And I think when we look at social media algorithms that you referenced at the very beginning of the book, I mean, this seems to be a great example where the objective function seems to be specified in a way that is relatively harmless. Hey, feed up the content that people seem to want to click on, and it seems to have consequences that are very different from, I think, what that principal would choose if the principal could choose in a reflective way.
Yeah, so you bring up a whole complex of issues, so I have to try to unpack these a little bit. So let me expand a little bit on what wireheading is. So it comes from some early experiments that people did initially with rats and subsequently with humans, where you can connect a wire directly into the pleasure center of the brain, and then give the organism control over putting an electrical signal in that wire. And they found with rats that the rat would rather just keep pressing this button and ignore food and drink and would drop dead after 48 hours of pressing the button. And when they did the experiments with humans, they found exactly the same thing, except they terminated the experiment after 24 hours. But literally, the person would sit there, they wouldn't get up to go to the bathroom. They wouldn't eat, they wouldn't drink, they would just sit there pressing the button. And well, so it's interesting to actually ask, well, why? Right? And the reason is that, well, why do we have a pleasure center in the brain? It was actually sort of for the purposes of reinforcement learning. And you mentioned the Baldwin effect earlier on. So the Baldwin effect is this idea that creatures learn during their lifetimes and attain a high level of fitness that way, and then they can be effective in reproducing and so on. And this may be better than producing fixed creatures who can't learn during their lifetime, because you can do many iterations of learning in one lifetime, whereas evolution gets to do one iteration per lifetime. And this has been proven mathematically to work, but you need a definition of learning during your lifetime, right? So that means that in the organism, there has to be an inbuilt signal of what is what is going well and what's not going well, right? And this is what our dopamine system and various other systems do, is tell us this is good or this is bad, right? They give a polarity to our experience, and we try to make it better, right? And unfortunately, this internal signal is a proxy, right? It's not what evolution really wants, right? Because it makes mistakes, and in particular, it gets stimulated by drugs and by electrical currents, and we wirehead because our system is built to pursue this signal of what's good or bad, regardless of whether it's actually good or bad. And so things go wrong. And same thing happens in markets, and as you point out with content selection, right? The algorithms are trying to maximize click-through, and so the algorithms have learned to become drug dealers, right? In that they have learned to supply you with content that makes you over time addicted, right? And then they can monetize you, and just like drug dealers, right? They give you the small doses, hey, just here's one for free, just try this, right? And because they know in the long run you will become a regular customer paying huge quantities of money, and in the click economy, you will become someone who clicks on all kinds of stuff that advertisers like you to click on, and you'll stay engaged with YouTube for hours on end, and et cetera, et cetera, et cetera.
But what's interesting is I think that if you're a user of the product, that might be the first approximation of the algorithm that you would choose, right?
So it's right. So it's the complication and a problem with the three principles that I outlined is that they assume that human preferences are fixed and stable, right? And so the next failure mode, so once you've got past the gorilla problem and the King Midas problem, right, the next failure mode, I don't have a good name for it yet, is where the machine learns to modify your preferences to be easier to satisfy.
Yeah.
Maybe you can't call it the politician problem, right? So,
well, it's an endogenous preference problem. Your preferences are endogenous, and they can be shaped over time.
Yeah, they can be manipulated, and so we can prevent that to some extent. So the solution for the simple wireheading problem, and people have pointed out that wireheading could arise in the real world with an AI system in the following sense, right? So if a human being is providing reward to the machine, and the machine is designed to maximize that reward, then the machine has an incentive to take control of that reward mechanism.
Mm-hmm.
So this is like, pressing the button on your own pleasure center, and force it to just produce maximum rewards at every time step. Right. So if the human is the one providing reward signals, then we just take control of the human, put some electrodes into the human's brain, force the human to, whatever definition of high reward, whether it's the human pressing a button or the human saying good job or whatever it might be, the machine will force the human to carry out that act over and over and over again. Right. And that's how wireheading arises in the human-machine relationship. So in a mild sense, that's what the content selection algorithms are doing. The machines have learned how to make you click over and over again because that's what it's designed to do. The basic reason why wireheading doesn't make sense is that the reward signal that a human, so a human saying good job is not the reward, right? In the way I've set it up, the reward is the human payoff function. And so actually taking over the human cuts off the supply of information about the human payoff function. And so, in fact, the algorithm has no incentive to do that, because as soon as you cut off the flow of information, the algorithm can no longer achieve its payoff function, which is sort of bound, it's tied, it's shared with the human, because it doesn't get any more information about what it is. So wireheading shouldn't happen here, but AI systems can still take actions that change human preferences. And the question is, should they do that? The second part of the problem is maybe even harder, which is, well, humans' preferences change anyway. And whose preferences is it supposed to satisfy? So it's going to act today. It's going to have, but that action is going to have an effect on the human tomorrow. It may be able to predict that your preference today for what tomorrow is like is going to be different from your preference tomorrow for what tomorrow should be like. So whose preferences should the machine satisfy, right? If you satisfy today's Greg, then tomorrow's Greg is going to be really annoyed. And if you satisfy tomorrow's Greg, then today's Greg is going to switch you off and say, how dare you not do what I tell you to do, right? And I don't think there's an obvious answer to this. And I know that philosophers have been writing papers recently about this. And economists have written some stuff about it as well. But it seems like there isn't a clear answer. And this arises, I think, quite a bit in bioethics, because people's preferences about what they want their life to be like can change dramatically pre and post operation. Let's say an amputation that leaves you in a wheelchair. Your preferences about how things should be afterwards may be quite different from what they are before. And it just creates real problems for doctors who have to help people make these decisions. So those are some of the things that sort of are really where we're asking ourselves, or how do we make progress? We're asking philosophers for help to clear these issues up.
Well, the other problem is that, even if each servant AI was doing its job and had solved the problem of optimizing the utility or whatever it was for each individual human being, we still are left with the problem of the overall aggregate human preferences. And political scientists and economists have yet to figure out how to aggregate preferences and figure out what it would be like to be compatible with humanity more broadly, as opposed to the preferences of individuals. And maybe those preferences are, the dictator of Korea's preferences rather than the preferences of you or me or someone more benign. And so is this something that we need to, you mentioned the way in which nuclear power has been something that we've taken seriously as a potential threat to the existence of humanity. You've talked about how, when it comes to genetics, there's been a concerted effort to, regulate the pursuit of research. Scientists have agreed to devise different codes and so forth. But it seems like in the world of AI, the winters that we've seen have been about loss of faith in the potential rather than in some concern about the having too much potential. Do you think that whatever brakes will be put on the development of this new intelligence will be imposed by kind of ethical concerns? Do you think that there is some prospect that a human compatible AI movement will help to shape and direct the future of research in this area?
I hope so. I think it's unlikely that, absent some huge catastrophe, we really ban research on AI. And as I mentioned before, just banning research on AGI and allowing research on tool AI doesn't help. Mm-hmm. The economic incentives to develop better and better decision-making technology are enormous. And if things go well, the upside is measured in quadrillions of dollars of value. So I don't think we can stop progress, but as happened with nuclear power, in fact, almost immediately. So it's a long story about how nuclear power got invented, but basically, one famous nuclear physicist, Lord Rutherford, said it's completely impossible, right? It will never happen. And the next morning, Leo Szilard invented the nuclear chain reaction. And he almost instantly realized that a nuclear chain reaction that was uncontrolled would lead to an explosion, just as a chemical reaction that generates more energy than it requires will cause an explosion, and that's well understood in chemical physics. So he realized that you needed a way to control this process if you were going to get useful energy out. So I'm arguing exactly the same thing with AI. If we don't control the AI, then we get basically an explosion. We lose control over our future. So we have to learn how to make controlled intelligence, right? So even though we're making systems that are more powerful than human beings because they have more ability to affect the world, greater decision-making, greater discovery capabilities than humans, we have to retain power over them forever. So how do you retain power over something more powerful than you? And I'm proposing a way to do that, just as Szilard, in fact, patented in 1934 a design for a nuclear reactor that maintained the reaction just below the critical level at which the explosion would begin, so that you could extract useful energy. And so what the book is about is, here's a design, kind of like Szilard's design for the nuclear reactor, that will allow you to have as much intelligence as you want without incurring the risk. So at the same time, I think, we have to catch up, right? Because the old way of doing AI, where you plug in the fixed objective, right? The fetch me a cup of coffee kind of AI, that's had a 70-year head start. So this in this new version, where there's explicit uncertainty about objectives, we have to develop all the the mathematical frameworks, the algorithms, the complexity proofs, the software, the demonstrations, and so on, and do that fairly quickly. But once that's done, there's no disadvantage to doing AI within this framework. In fact, I think there are many, many advantages. The kinds of behaviors you can generate within this framework are things that we want, like AI systems that ask permission. Well, if the AI system knew what the objective was, it would never ask permission, right? Because it would just calculate the optimal solution for achieving the objective and do it. But you want systems to ask permission when they're about to do something that might be extremely harmful, right? So, the example in the book would be, if you're going to build a system that's supposed to restore carbon dioxide levels in the atmosphere, right? and it comes up with a plan that maybe removes a quarter of the oxygen, right? You want it to ask permission before doing that, right? Because in fact, the objective of restoring carbon dioxide levels is not the objective. We care about more than just that, right? In particular, we care about having enough oxygen to breathe, right? And another solution that turns the oceans into sulfuric acid, right? Is that a good idea? Well, I want the AI system to ask me if it's a good idea before doing it. So you'll get systems that are much safer, much more robust, much more adaptive to the user, more cautious in areas that they're less certain about your preferences. And all of these things are desirable, and they'll make for better products. So in that sense, we could have a nuclear industry, and we just have to hope we don't have any Chernobyls.
Yes. Well, I think we barely even scratched the surface of the text. I think it's an extraordinarily rich book, and it touches on philosophy, it touches on economics, it touches on sociology, it touches on control theory, operations research, a lot of different disciplines. A fascinating book, highly recommended. Stuart, thanks so much for joining me. I appreciate it.
It's a pleasure, Greg.
Hopefully I'll see you in person, even though you're only probably a mile away from me right now. I'll hopefully see you in person at some time soon.
Yep, and you can ask me for a cup of coffee, and I won't spend a week. I won't spend a week fetching it either. All right.
Excellent. I look forward to it.
This is Unsiloed, brought to you by Alumni FM, connecting people through stories.